Hello, my name is Brian Payton, and in this presentation I'll be presenting my work on an algorithm which I'm calling a generalized label correcting method for optimal kinodynamic motion planning. So let me begin by answering the question, what is optimal kinodynamic motion planning? So the standard formulation of the problem, we're given some representation of the environment, a starting configuration or state for an autonomous robotic system, and a set of goal states that we'd like to reach. The problem then is to compute a continuous motion starting from the initial state and terminating at one of the goal states that avoids contact with the environment. Secondly, we'd like this motion to satisfy differential constraints that come from a dynamic model of the system. And then since there is generally not a unique trajectory satisfying these constraints, we'd like to compute one that minimizes some cost functional. So we can formulate this problem mathematically as a nonlinear optimization. So we'd like to compute a trajectory x that at each instant in time t belongs to a set of admissible states, x free. At the initial time t equals 0, the trajectory has to be at an initial state, x0, and at the terminal time, the trajectory has to be in the goal set, x goal. Secondly, we also need to compute a reference control signal u that is constrained at each instant in time t to belong to a set of admissible control inputs omega. And then the dynamics of the system are encoded by a first order differential equation that also gives us the relation between the input signal u and the resulting trajectory x. And finally, the cost function we will assume takes the form of an integral of a general running costs g. So that's the problem formulation as a nonlinear optimization. So why is this an important problem? Virtually every autonomous robotic system uses some form of motion planning, and the increasing use of autonomous robots in a broad range of industries creates a need for efficient and general purpose motion planning algorithms that can be applied to any one of these applications with a minimal amount of application specific development. So this talk will be outlined as follows. I'll start with some literature review in motion planning and cover some of the state-of-the-art algorithms. Then I'll move on to the main contribution of this presentation, which is the generalized label correcting method. And then in the second part of the presentation, I'll focus on admissible heuristics for optimal kinodynamic motion planning. And these techniques will complement the generalized label correcting method, as well as any other motion planning algorithm that might be developed in the future. And then I'll wrap up with some discussion about extensions and future work. So early research in motion planning focused on a simplified version of the problem known as the generalized movers problem. And it was discovered early on that this problem is p-space hard with respect to the number of degrees of freedom of the system, or equivalently the dimension of the state space. And what this means is that the most efficient motion planning algorithm that could be designed to solve this problem is going to have complexity that grows rapidly as we increase the dimension of the state space, or the number of degrees of freedom. So then some years later, a complete algorithm was developed which achieved exponential complexity, and this is basically the best we can hope for in terms of a complete motion planning algorithm. But then there's still a need for practical real-time motion planning algorithms that can be used on complex systems. So this motivates coming up with relaxations of completeness. So in this context, we'll say an algorithm is complete if it determines in finite time whether or not a feasible solution exists, and if there is one, it will give us one example of a feasible solution. And then what turned out to be a very useful relaxation of completeness is probabilistic completeness, which applies to randomized algorithms that generate candidate trajectories by randomly sampling from some space. And so an algorithm is probabilistically complete if the probability of computing a trajectory, feasible solution when one exists converges to 1 as the number of random samples tends to infinity. But when there is no feasible solution, the algorithm will run forever without terminating. And then an analogous relaxation of completeness is resolution completeness, which applies to algorithms that use a numerical approximation of the problem. And then we say an algorithm is resolution complete if it finds a feasible solution when one exists, as long as we used a sufficiently high resolution. But then if we don't use a sufficiently high resolution, the algorithm may incorrectly decide that there is no solution. So the first big breakthrough in these approximate motion planning algorithms was the probabilistic roadmap. So the advantage of this algorithm is it's very effective in practice and also incredibly easy to implement. And so the way this algorithm works is you randomly sample a bunch of points from the state space, and then for each of these points you locate a fixed number of that point's nearest neighbors, and then you connect those points with an edge. And then this forms a graph over the free space which approximates the feasible motions in this particular environment. So then we can do approximate motion planning queries by solving shortest paths on this graph. And now the main limitation of this algorithm is that it requires a local planning subroutine to make these connections between randomly sampled points. And this complicates the implementation of the algorithm on systems that have non-trivial dynamics because it's not immediately clear how we can make these point-to-point connections. So in response to this limitation, the next big breakthrough in motion planning was the rapidly exploring random tree. And the way this algorithm works is that it builds a tree of candidate trajectories rooted at the initial state by randomly sampling from the state space, then locating the nearest vertex currently within the tree to the randomly sampled point, and then extending the tree from that nearest vertex. And now that it doesn't need to make exact connections to the randomly sampled state, so this makes the algorithm much easier to implement on systems with complex dynamics. But a limitation of both of these algorithms is that neither one will generate or converge to an optimal solution as you increase the number of random samples. So then the next big thing in motion planning was the optimal variance of these algorithms, the RRT star and PRM star algorithms. And so these variants of the algorithms now have probabilistic completeness as well as asymptotic optimality. And so the way this works for the RRT star algorithm is that you expand the search tree with the usual iteration of the conventional RRT algorithm. But then from this new vertex, you locate within a neighborhood of a very specific radius all of the nearby vertices. And then you locally rewire or optimize the graph inside this neighborhood to minimize the cost of the paths from the root to these vertices. And now the size of this neighborhood is sufficiently large so that the algorithm will converge to an optimal solution, but it's also small enough that the complexity is essentially the same as that of the standard RRT algorithm. But now in getting this asymptotic optimality property, we once again require a local planning subroutine to make these point-to-point connections for the rewiring procedure. Nonetheless, this algorithm, these optimal variants of these algorithms had tremendous impact, and it stimulated a lot of work on the local planning problem. So the first line of defense in trying to apply the PRM star or RRT star algorithms is to try and justify using a dynamic model and cost function for which we have a closed form solution for the local planning subroutine. And two popular examples of this for wheeled robots is the Dubin's paths and the Reeds and Shep paths. Alternatively, for linear systems, we can use classical steering solutions from linear systems theory. And for nonlinear systems, those which have this property of being differentially flat, we can solve the local planning subroutine fairly easily by solving a linear system of equations. And now the issue with these latter two approaches is that they do require a significant amount of computation, for example, computing a matrix exponential or solving a linear system of equations. And this may not sound like a very difficult computation, but you have to keep in mind that when you run these motion planning algorithms, you have to call the local planning subroutine tens or hundreds of thousands of times. So there's still some need for an algorithm with nice completeness and optimality properties, but which doesn't use a local planning subroutine. And one of the recent contributions in this direction is the stable sparse RRT algorithm. So this algorithm is asymptotically almost optimal and and probabilistically almost complete. Um, it will converge to a solution with bounded suboptimality, and then this bound can be made arbitrarily small by adjusting some tuning parameters in the algorithm in exchange for a slower convergence rate. And while this algorithm is a nice theoretical contribution, its runtime um, is not really practical for real-time applications. So we still need an algorithm that's fast enough for real-time use. So this is where I'll start talking about the algorithm I've been working on, the generalized label correcting method. So this algorithm is a resolution complete algorithm that is asymptotically optimal, and it's I would argue has a sufficiently fast runtime for a number of real-time applications. So here I'm showing a benchmark on an acrobat swing-up problem. The acrobat is a nonlinear underactuated system with fairly complicated dynamics, and this makes it very difficult to implement, for example, the RRT star algorithm to solve this problem. But what's nice about the SST and GLC methods is that all you need to provide is a cost function and a dynamic model, and the algorithm will converge to an optimal solution, or at least an approximately optimal solution. And then what sets the GLC method apart from the SST algorithm is a considerable reduction in runtime that puts the runtime in the neighborhood appropriate for real-time planning. So now I'll spend some time discussing the mechanics of the algorithm and hopefully convince you that it's a very simple algorithm to implement, much like a lot of the other classical motion planning algorithms. So it relies on a partition of the state space into these rectangular regions. And then at each iteration of the algorithm, we use a finite number of control inputs to forward simulate the dynamics for a fixed interval of time. And then we note the regions that these trajectories terminate in, and then label these regions with the cost of those trajectories. Then we can push these trajectories to a priority queue, so that way we can repeat this process. And another important feature of the algorithm is that when a trajectory terminates in a region which is already labeled with some cost, if the cost of the new trajectory is less than the cost of the current label for that region, then the label of that region is corrected with the lower cost. Alternatively, if the new trajectory has greater cost, then we determine that it is a poor candidate for an approximately optimal solution, so we discard that trajectory. And then we just continue this simple iteration, and the algorithm will fill the space with a tree of approximately optimal trajectories until a trajectory terminating in the goal set is found, at which point the algorithm can terminate. So there's a few key ingredients to this technique to get these optimality and completeness properties. So the first is this finite collection of control inputs that we have to choose to forward simulate the dynamics with. Secondly, there's the duration that we forward simulate the dynamics with each of these control inputs. There's also a time horizon limit for the algorithm at each resolution. This is equivalently a depth limit to the search tree. And then also the size of these rectangular regions. So now I'll spend some time discussing the details of each of these aspects of the algorithm. So let's say this orange blob is our set of admissible control inputs omega. And omega r is the finite collection of control inputs we've selected for a run of the algorithm at resolution r. All that's required of omega r is that the dispersion of omega r within omega converges to 0 as we increase the resolution. And all this means is that the radius of the largest sphere centered at a point in omega, which has empty intersection with omega r, is converging to 0 as we increase the resolution. And to argue that this is not difficult to accomplish, we can do this just by randomly sampling from omega. Next, we need the intervals that we forward simulate the dynamics with for each of these control inputs to be inversely proportional to the resolution. And then the number of time steps, h of r, that determines a time horizon limit needs to grow sufficiently fast so that the duration of control inputs that we can consider grows without bound. And then with this simple construction, we can show that we can approximate any measurable function with any finite time duration in an L1-like distance metric. So this means we have a good numerical approximation of the input signal space. And now the next thing we need to worry about is how well we can approximate the input signals that generate actual solutions to this problem. And this requires that we gain some understanding of the topology of the set of solutions. So to state the next result, I need to introduce some new notation. So let's say U is the set of all measurable input signals with finite duration that we're considering. And then U sub R is this finite approximation that we have just constructed. We'll call U free the input signals that generate trajectories that remain in the free space for all time. And then U goal will be the subset of U free consisting of trajectories consisting of inputs generating trajectories that additionally terminate in the goal set. So now an additional assumption that we need to impose on our algorithm is that the free space and the goal sets need to be open sets in the standard topology. And then with this assumption, what we can show is that as we increase the resolution, the minimum cost input signal from our approximation, which is also satisfying the motion planning specification, will converge to the optimal cost for this problem. So that's good. So we have a way of numerically approximating the optimal solution. So we could, in theory, get an approximately optimal solution by enumerating this set UR. But in order to do this efficiently, we have to use this pruning step where we discard, we relabel the regions with the appropriate costs, and then we discard poor quality trajectories so we don't evaluate an excessive amount of subtrees. So the next question we need to ask is, how does the resolution govern the size of these rectangular regions? So the short answer is that if we choose the side length as a function of R to satisfy this asymptotic constraint here, L sub f is a Lipschitz constant on the dynamic model, then the algorithm will be resolution complete and asymptotically optimal. And what I mean by asymptotically optimal is that as we increase the resolution of the algorithm, the output will be converging to the optimal cost for the problem. So I'll skip the fine details of the proof, but essentially it parallels the standard proof of completeness for a best first search algorithm on a graph. But then we also have to incorporate this numerical analysis because we're doing a finite approximation of a continuous problem. So what we do is we kind of slice up the goal region into layers of a carefully specified thickness. And then we consider the minimum cost input or minimum cost trajectory terminating in this innermost layer of the goal region. And then we can calculate a bound on the error between the true optimal cost solution and the cost of this trajectory. And then what we do is we reason about, or we suppose that maybe this trajectory gets pruned from the search at an early iteration by some other trajectory. And then what we can do is use Gronwall's inequality to argue about how we can extend this second trajectory to also terminate in the goal region, but now in the second layer down in the goal set. And then we can also use some continuity arguments to bound the error in cost between this second trajectory and the first. And then we start wrapping this up into an induction argument. So we continue this procedure, and since there's a finite depth to the search tree, we can calculate a bound on the suboptimality of the output of the algorithm. And then we ask, what is required of the size of these rectangular regions to guarantee that the thickness of these layers of the goal region are going to collapse down to zero, and also so that the numerical error in cost will converge to zero. And then what falls out of this derivation is the expression shown above. So now I'm going to show a few examples to illustrate the types of problems we can solve with this algorithm. So in this example, I'm showing a wheeled robot navigating a reasonably cluttered environment. And what's nice about the GLC method is that we can consider whatever cost function we like. So while a lot of algorithms use shortest path objective, which generates very tight radius turns around obstacles and also has rapid changes in curvature, which will result in large lateral accelerations and jerk. That'll be uncomfortable to passengers if we're considering planning for, say, an autonomous vehicle. If we now we can consider a mixed penalty on the path length and also an L2 penalty on the curvature of the path. And then what we get is this, the path shown in the figure, which has much more gradual changes in curvature and resembles the path you would expect a human driver to execute. And then as far as runtime goes, in about 3 milliseconds, we can generate a feasible solution on a laptop. And then as we increase the allowed runtime, we can generate higher quality solutions that we know from the theoretical results will converge to the optimal solution. And so here's a significantly different example to kind of illustrate the flexibility of the algorithm regarding the dynamic model. So this is a thrust-limited point robot with a nonlinear aerodynamic drag, and this is in the simulated indoor environment. The task is to go from one room to the other through a small window. So in the top row, I'm showing a low resolution run of the algorithm. So we get a solution very quickly, but it's a very suboptimal solution. And I'm also using randomized control inputs. So you see there's variance in the output of the algorithm because of these randomized inputs. But then from top to bottom, there's increasing resolution. So it takes longer to calculate the solution, but the output is converging to the optimal solution. And indeed, what the figure shows is a trajectory that resembles what you would expect the optimal solution to look like. And so for the runtime in this example, we see that it takes several seconds to generate a good quality trajectory. And this is because this system has 6 states, which is considered a relatively high dimensional state space for a motion planning problem. But now if we consider running the algorithm with an admissible heuristic and to guide the search, we can speed up the runtime of the algorithm by another order of magnitude or so. And this once again puts us kind of in the ballpark for real-time applications. And so this brings me to the second part of the presentation, which is tools for the analysis and construction of admissible heuristics for the optimal kinodynamic motion planning problem. So in a general search problem, a heuristic is any kind of rule that tells us where we should look next in a systematic search. But an admissible heuristic has a very precise meaning. It's a function that assigns to each state an underestimate of the optimal cost to reach the goal. And then the optimal cost to reach the goal is a function that gives every state, the cost of the shortest path or the optimal trajectory to the goal. In this graphic here I'm showing in the slide, it's a simple shortest path problem. And for these problems, an obvious heuristic that gets used all the time is the Euclidean distance from the initial state to the goal, because the length of the straight line connecting an initial state to the goal is shorter than the shortest path in the presence of obstacles. So here I'm just illustrating further that this Euclidean distance heuristic is indeed an underestimate of the optimal cost to go. So the graphic on the left shows the optimal cost to go in this environment. So you see that it gets a little distorted on the backside of the obstacle. And then on the right, I'm showing the Euclidean distance heuristic next to the optimal cost to go. And you see the Euclidean distance heuristic shown in green is below the optimal cost to go shown in blue. And what's kind of interesting is that since the Euclidean distance heuristic ignores the presence of the obstacle in the environment, you see this accumulated gap between the optimal cost to go and the Euclidean distance heuristic on the backside of the obstacle. So the reason why this definition of admissible heuristic is useful is that if we have a segment of trajectory and look at the cost of that segment of trajectory plus our estimate of the remaining cost to go, if we see that that exceeds the optimal cost from the initial state, then that segment of a trajectory is certainly not part of an optimal trajectory, so we don't need to consider extending that trajectory any further. So in practice, we don't actually have the optimal cost to go, so we usually have to rely on some upper bound that is available, and then we just check this inequality using that upper bound in an attempt to narrow the search to only good candidates. Another even better way to make use of an admissible heuristic is to just order our candidate trajectories according to the cost plus the admissible heuristic. So here's this shortest path toy problem once again. Here on the left, I'm showing a heuristically informed um, run of a motion planning algorithm, and on the right is just a uniform cost search which doesn't make use of a heuristic. So you see on the left, the algorithm expands much fewer states before it finds a trajectory to the goal. And what's interesting is that where this heuristic where the heuristic was least effective in informing the search was on the backside of the obstacle, where we saw there was this accumulated gap earlier between the optimal cost to go and the heuristic. So so Euclidean distance works great for shortest path problems, but we're interested in the optimal kinodynamic motion planning problem. So we have a general dynamic model and cost function. So now it's non-trivial to verify that some heuristic is less than the optimal cost to go, since we don't have the optimal cost to go in advance. So just to remind you, the problem formulation on the top of the slide, we had the cost function was mostly defined by this running cost g, and the dynamic model was determined by this function f. And so a condition that I found to be very useful for analyzing handcrafted heuristics for a particular problem is the following. We first check if the heuristic is less than or equal to 0 in the goal set. And secondly, we check that the inner product of the gradient of the heuristic with the dynamic model plus the running cost is greater than 0 on the free space minus the goal set. And then if these conditions are satisfied, the heuristic is an admissible heuristic. So let's just do a sanity check and make sure that the Euclidean distance heuristic for the shortest path problem satisfies these conditions. So in this framework, the shortest path problem takes the following form. The trajectory x integrates the input signal u directly, and then we restrict the input signal u to the unit sphere, so that way the trajectory has unit velocity. And then the running cost for this, in this case, is just 1, which gives us a minimum time objective. And since the trajectory has unit velocity, this is also going to give us the shortest path. So if we take the goal set to simply be the origin for simplicity, our heuristic will just be the Euclidean norm of the current state. So now we just plug this into our admissibility conditions. So the norm of x at 0 at x equals 0 is 0. And now for the second condition, the gradient of the norm of x is x divided by the norm of x. And then we take the inner product with the dynamic model, which is just u. And then we add the running cost, which is just 1. So then we can expand this inner product with the Cauchy-Schwarz inequality. So we have minus norm x divided by norm x, which is going to be 1, times norm u, which is by definition 1, and then plus 1 is greater than or equal to 0. So it works out for the Euclidean distance heuristic. So now one observation that I've noticed that was a cause for concern is that not all admissible heuristics satisfy this condition. So it's just a sufficient condition for admissibility. So this raises the question, are there always good heuristics in this set? And if so, how might we optimize or select a good heuristic from those satisfying this condition? So let me answer the second point first. And so recall that we saw that the heuristic was least effective where there was a large gap between the optimal cost to go and the heuristic, right? Because we expanded a large number of states on the backside of the obstacle when we used an informed search using the Euclidean distance heuristic. So this suggests that we want to, while maintaining this admissibility condition, get the heuristic as close to the optimal cost to go as possible. So one way of doing this is just to try and formulate an optimization. So let's just try and maximize the integral of the heuristic over the free space, subject to the admissibility conditions. And what's interesting about this optimization is it's actually a linear program, or an infinite dimensional linear program, because you see this objective is linear in h, and then both of the constraints are actually affine constraints in H. And now for the first point, which is, are there any good heuristics in this set? So if we solve this linear program, will we have anything that's a heuristic of any use? And so to answer that question, let me just remind everyone of the Hamilton-Jacobi-Bellman equation, which is a cornerstone of optimal control theory, because if we solve this nonlinear PDE and get a solution V, that solution V will be the optimal cost to go. So to answer the first question, we have the following equivalence theorem or duality theorem that says that a function h is a solution to the linear program if and only if it is a solution to the Hamilton-Jacobi-Bellman equation. So that's a pretty cool observation. It also tells us that this formulation is a reasonably good one. So if we solve this problem, we'll have the exact optimal cost to go. But now one will ask, well, the Hamilton-Jacobi-Bellman equation is hard to solve in general, so it's probably the case that this linear program is hard to solve. And that is indeed true. But what's useful about this formulation is that every point on the feasible set of this linear program represents an admissible heuristic. So even if we can just compute an approximate solution, it'll probably be a very good heuristic for any motion planning algorithm. So as a way of computing an approximate solution, I will first propose that we restrict our attention, our candidate heuristics, to a finite dimensional polynomial subspace. And what this does is it'll turn this, our infinite number of parameters, or this optimization objective, into a linear optimization objective over a finite dimensional space. And then if we additionally assume that the dynamics and running cost are polynomial functions, which is a little bit restrictive, then the constraints become polynomial inequality constraints. And while this is NP hard to check in general, polynomial inequality constraints lend themselves very nicely to sum of squares approximations. So if we just replace the inequality constraint with a sum of squares constraint, this entire problem gets turned into a semi-definite program, which we can solve to arbitrary accuracy in polynomial time. So now we have more or less a complete framework for analyzing and constructing heuristics for the optimal kinodynamic motion planning problem. So let me just give one example where we can run this sum of squares optimization. Let's look at the double integrator with the minimum time objective to the origin. This is a well-known problem where the closed form solution for the optimal cost to go is available in closed form. So here in the graphic, I'm showing in the red contour is the exact optimal cost to go that we can calculate by hand. And then each of the contours below show the output of this sum of squares optimization, where we consider all the polynomials of increasing degree. So as we increase the degree of the polynomials in our finite dimensional basis, we have a more rich approximation of the space of differentiable functions. So we get a better approximation of the optimal cost to go. And then we also have, a certificate that tells we can prove that the output of this optimization is an admissible heuristic. So that covers the main contributions of this work, and now I just want to spend some time going over some extensions and possible future work. So I think the natural next step is to consider more complex specifications than the standard motion planning problem. Specifically, I'm interested in looking into specifications in linear temporal logic. And so let me just give an example of what I'm thinking. So let's say instead of avoiding obstacles and eventually finding the goal, we want to consider, let's say, rules of the road for motion planning for an autonomous vehicle. So let's just look at this example where we have a crosswalk with a stop sign on a one-way road. And we want to impose the rule on the motion planner that the car shouldn't drive backwards, in the wrong direction, and it should stop at the white line before going into the crosswalk, among other rules. So the first thing we want to do is identify the atomic propositions for this rule. So we might say stopped, line, backwards, and crosswalk. And then what we'll do is repurpose the existing collision checking functionality to determine from any particular state of the vehicle whether each of these propositions is true or false. And just to illustrate this, here I'm showing a 2D state space for the vehicle. So the horizontal axis is the vehicle position in the lane along the road, and then the vertical axis is the vehicle speed. So the red band shows states where the velocity is negative, so the vehicle would be moving backwards, which we don't want. So backwards would evaluate to true. The purple band is an artificially thickened region where the velocity is 0, so stopped equals true. The yellow band is where we define the vehicle to be more or less in front of the white line. And then the green band is where the vehicle is, where we would define to be in the crosswalk. So then what we can do is turn this specification into an LTL specification. So we can say always not backwards and not crosswalk until line and stopped. And then we can take this LTL formula and transform it into an LTL monitor, which is a deterministic finite automaton that accepts finite traces of these propositions and will tell us whether or not we are falsifying this formula with a particular finite trace. So then we can basically just cut and paste this LTL monitor into the motion planning algorithm where we normally had the collision checking functionality. And now the algorithm will generate the optimal rule-abiding trajectory. So we see here the output of the GLC algorithm starting from some zero velocity before the crosswalk. So the red contour shows the state space trajectory. So the vehicle accelerates up to some top speed and then decelerates down to 0 in the yellow region where we define the line, the vehicle to be in front of the line. And then after stopping at, in front of the line, the vehicle takes off again through the intersection. So now just to summarize the contributions of this work, the first part of the presentation focused on the generalized label correcting method, which was an efficient resolution complete algorithm for optimal kinodynamic motion planning. And the main advantage of this algorithm is that it only requires a dynamic model instead of a local planning subroutine, which makes it much easier to implement in a large range of applications. And then the primary assumption of the algorithm was that we needed the free space and goal sets to be open in the standard topology, which is not a particularly restrictive assumption. And then in the second part of the presentation, I presented some new tools for analyzing admissible heuristics for the optimal kinodynamic motion planning problem. So I first presented just some admissibility conditions that let us check admissibility for, say, handcrafted heuristics when we have some intuition about the problem. But then I used these conditions to formulate a linear optimization and found that it was equivalent to the Hamilton-Jacobi-Bellman equation. And then as a computational procedure for computing an approximate solution, I propose that we approximate this linear optimization as a sum of squares program and provided an example of that. So thank you for your attention. That's it.